Hello. In this presentation, this is the second in the chapter on organometallics. So in this presentation, I'll be talking about two reactions that both Grignard reagents and organolithium reagents undergo. They behave exactly the same way in these two reactions. So you could either use a Grignard or you could use an organolithium, whichever you happen to have handy. Or if you want to just outline a synthesis problem, you can choose either one. Of course, typically you'll have to make them, and you make them differently. Remember, you make Grignard reagents from an alkyl halide plus magnesium. You make organolithiums from an alkyl halide plus lithium. So, first reaction. Again, we're going to look at two reactions here. The first one is actually pretty simple, and I talked about it in the first video, so you might want to go back and review that briefly. But basically, it's what I would refer to as a bad reaction. It's talking about the fact that both Grignards and organolithiums both react with protic materials, that is, acids like HCl or carboxylic acids, or for that matter water, alcohols, and even alkynes that have that hydrogen on the end are strong enough acids to react with organometallics. So in each case, a different organometallic is going to react with either water or an alcohol or a carboxylic acid, or even technically, like I said, an alkyne. But typically these are the ones that you would use, and especially with water, it's usually not a desirable thing. So the point is that we want to keep water and these other things away from our Grignards and away from our organolithiums, because they do bad things to them. And here's the bad thing that they do. So if you start with a Grignard like this and you react it with water, what does it do? The organic part of it, the alkyl group, pulls off an H plus from the water, and it becomes an alkane. So a propyl magnesium bromide becomes propane. That's pulling off an H plus. From here, of course, that leaves hydroxide, and the counterion for the hydroxide is the magnesium and the bromide. So you end up with magnesium and bromide and hydroxide. So it's to be a mixed ionic compound with magnesium plus 2, a bromine minus 1, and a hydroxide minus 1. That typically would be a ionic compound, and you would just get rid of it. So notice the problem here is that you get a compound, propane, which you would typically not want to get after having spent a lot of time and effort making a Grignard in the first place, to just get propane. So again, not a desirable reaction. Same thing would happen if you had a Grignard with an alcohol. Again, the carbon group would pull off an H plus from here, and that carbon was a CH2, is now CH3, just pulled off a hydrogen from there. So again, you're just making the hydrocarbon compound, essentially destroying this functional group. And in this case, the counterion would be the methoxide that's left over from here, and a magnesium and chloride, and again a mixed ionic compound which has methoxide, magnesium, and chloride in it. Here's exactly the same kind of process, just a slightly more complicated case, where in this case we have a methoxy group attached to the carbon group of the Grignard. Remember, in the first video I talked about the fact that ethers are okay to have in Grignards, as are double bonds for that matter. So this is fine, it's just part of the whole Grignard reagent. But again, this is an acid, so this base, in other words that carbon, is going to pull off the H plus from this acid and just put a hydrogen on there. So you've essentially gotten rid of this group and just put a hydrogen on to make a much less valuable compound. So again, it's typically not something you're going to want to happen. But if it did, this base would pull off the H plus from here. You would get the carboxylate, in other words a negative oxygen here, as the conjugate base of this acid, and the counterion for that negative oxygen would be the magnesium and the iodide from here. So again, you get a mixed ionic compound. But the point is, you're making a new organic compound, which is typically not as valuable as the one you started with. So you're not going to want to do this, but you need to be aware that it could happen. These three reactions are exactly the same as these three reactions, but instead of starting with a propyl magnesium bromide, a alkyl magnesium chloride, or a cycloalkyl magnesium iodide, we're starting with lithiums in each case, but it's the same process. In each case, you get a ionic compound as a byproduct and the same organic compound, again less valuable than the starting material, and so therefore typically not something you're going to want to do. So that's the first reaction. The second reaction of Grignards and organolithiums is a much more useful one. In this case, what we do is we start with the Grignard, and we add a compound called an epoxide. Now you may remember epoxides, those are three-membered rings with an oxygen. We came across them last semester in the reaction on alkenes. You learned how to make epoxides, and just to remind you, you make them from alkenes by reacting with that funny reagent called MCPBA, which stands for metachloroperbenzoic acid. It's just a way of making epoxides from alkenes. But in this case, what we're doing is starting with the epoxide, and we're reacting it with a Grignard, in this case N-propyl magnesium bromide. And what you end up with is that N-propyl group from the magnesium group attached to the CH2, that's this, and then the CH2, that's this, and then an O- that comes from this oxygen. Okay, so it seems like a complicated reaction, but it's really not. If you look at the mechanism, and I've outlined the mechanism here, it's really just an SN2 reaction where the carbon of the Grignard acts like a nucleophile, and it comes in and attacks the backside of the epoxide at one of the two carbons of the epoxide. And by the way, if the two carbons aren't the same as each other, it attacks at the less crowded carbon, which is nice. But that's what it does. It attacks the back of this carbon and pushes out the oxygen as the leaving group. Now we're used to halides as leaving groups. In this case, it's the oxide as the leaving group. And the reason it can act as a leaving group here is because that three-membered ring is highly strained, and that bond, really not that good a bond. So as soon as this attacks, you can open up that bond, put that pair of electrons onto the oxygen, and that relieves the strain of the three-membered ring. So that's the driving force here. So in essence, whatever our group is, it's attached to the magnesium, attaches to one of the two carbons, the less crowded of the two carbons in the epoxide, opens up that bond that was attached there, and that then leaves the oxygen attached to the second carbon. So if the carbon group of the Grignard attaches to this carbon, the second one is the one that ends up with the oxygen. This is what we call an alkoxide. And its counter ion would be the magnesium bromide, so that group right there is ionic, and it ends up counterbalancing the negative oxygen on the alkoxide. And notice we've dealt with alkoxides before. They're fairly familiar to us. They're essentially the conjugate bases of alcohols. And we've learned what about alkoxides? Well, they are in themselves strong bases. And so they can do eliminations on other alkyl halides. They're also good nucleophiles, so they can do SN2 themselves. But in essence, we're making an alkoxide in this case by making a new, what? What's the new bond between that carbon and that carbon? Right there. It's a carbon-carbon bond. And so this is a very useful reaction. Notice I put a star by it here. It's a carbon-carbon bond making reaction, and we pointed those out in the past as being good things to keep in mind because you can use them to build up bigger carbon skeletons from smaller skeletons. So you make alkoxides by reacting a Grignard reagent with an epoxide. Here are a couple of other examples. This is the one we just did. N-propyl magnesium bromide reacts with ethylene oxide to produce this new alkoxide with a new carbon-carbon bond right there. But what if the Grignard that we started with was a lithium instead? Same thing. Remember I said that Grignards and organolithiums do essentially the same reactions. So this is a 4-carbon, 1, 2, 3, 4 chain with a lithium on the end, and it happens to have a double bond in it. Again, double bonds are perfectly fine in organometallics, so the fact that there's a double bond in this is pretty much irrelevant. That carbon right there that has a lithium attached to it is going to become bonded to one of these two carbons of the epoxide. So which one is it? The less crowded one. So in other words, that carbon right there. So that carbon becomes attached to that carbon. This carbon-oxygen bond opens up, becomes O negative, and that's this O negative here. So notice that these 4 carbons, 1, 2, 3, 4, were the carbons that came from the organolithium. And then these 3, 1, 2, 3, were the ones that came from the epoxide. And that bond opened up, and that became O negative. This bond is still there, and so that O negative is attached to that carbon, which is that carbon. So we now end up with a chain that's 1, 2, 3, 4, 5, 6, 7 carbons long. The 4 from this group and the 3 from that group becomes this alkoxide. Again, just to remind you, that's an SN2 mechanism. This carbon comes in, attaches to that carbon, pushes out that oxygen all at the same time. So it's an SN2 type mechanism. And here's another example. If your Grignard reagent is cyclopentyl magnesium iodide, and your epoxide is this one that has just a CH2 at that position and a CH with another group on it, in this case happens to be a vinyl group, then it's going to attack the less crowded carbon, and that carbon will become attached to that carbon. So this is a new bond here. That carbon became attached to that carbon. This bond opened up and became O negative. The rest of this group is still there, unaffected by the reaction. So again, we get an alkoxide from the reaction. The counter ion to the alkoxide in the first one was magnesium bromide. The counter ion in this case was a lithium. In this case, since we're using a Grignard, the counter ion here would be magnesium iodide. But again, this is a very useful reaction because you're making carbon-carbon bonds, and you can make fairly sophisticated skeletons from pretty simple starting materials. Once you've made the alkoxide by that Grignard reaction or organolithium reaction, what can you do with it? What can you do with alkoxides? Well, typically what you're going to do is follow it up with either adding a dilute acid into it, which turns the alkoxide back into the alcohol. So this is a really good way of making alcohols. Essentially, you do the Grignard reaction with the epoxide, and then you just treat it with dilute acid and work up, and it returns an alcohol. So you make an alcohol with a bigger skeleton. Or alkoxides can also be nucleophiles. So remember the Williamson ether synthesis? That was starting with an alkoxide, treating it with an alkyl halide. Again, in SN2, the oxide comes in, attacks the backside of that carbon, and pushes out the halide. And so there's the halide, and then what kind of compound do you get? Well, the fact that this is a Williamson ether synthesis suggests that might be an ether, and it is. In fact, you know that an oxygen with 2 carbon groups on both sides is an ether. So normally, after you've done the Grignard with an epoxide to make a new alkoxide, then you're going to either add acid to it to make a new alcohol, in which that O- just becomes an OH, or you're going to react it with a usually primary or methyl alkyl halide, and that's going to stick this new group onto that oxygen, and so we end up with an ether. So what I'm telling you is once you've made the alkoxide, you can either put an OH on that carbon, or you can put an OR group on that carbon, so you can make either alcohols or ethers by following up the Grignard with whatever of the 2 possible reagents you might want to choose. So here's another example. If we started with this alkyl lithium, react it with this epoxide, you would get this alkoxide, and then you could either add acid in the second step to make that into an OH, or you could add an alkyl halide in the second step to make that into an ether. And then here's another example. Again, we saw the cyclopentyl magnesium iodide plus the epoxide gives you this fairly complicated looking alkoxide with an O negative. Again, if you add H plus to it, it just becomes, that O minus becomes an OH. Or if you add, say, an ethyl bromide or some other primary or methyl halide, you would then stick that carbon group onto the oxygen and make an ether. It would be a very useful reaction in synthesis. So what I would like to do at this point is discuss the steps that you might use to make a particular alcohol or ether, which we've seen typically you end up with after a Grignard reagent. So let's try this. What I'd like you to do is outline the steps in an efficient laboratory synthesis of this particular compound, which happens to be an ether, from any alkyl halide and from an epoxide. Okay. Now you might stop and think, if you're thinking critically, don't you have to have a Grignard reagent to do this, or an organolithium to do this? And the answer is yes, you do. So therefore, since you're not allowed to start with a Grignard or an organolithium, you're going to have to make it from an alkyl halide, but you know how to do that. So let's put it all together here. First thing you're going to want to do is determine, is the product an ether or is it an alcohol? And the answer is, in this case, it's an ether. So you're going to want to draw the alkoxide that that's going to come from, and then add in methyl bromide to make it into your ether. So go ahead and write down that step, see what you would come up with, and then we'll switch to the next screen and you'll see the answer. Okay, so since this is our target molecule, we're going to want to start with that as the alkoxide. And in this case, we're going to add methyl iodide to put a methyl group on there. Now here's a little bit of a practical thing to keep in mind. If you want to put a methyl group onto an alkoxide, you're going to want to use an alkyl halide. But if it's a methyl group you're using, typically you're going to want to use iodide rather than bromide or chloride as your halide, and that's simply because methyl bromide and methyl chloride are gases, and they're much more difficult from a physical point of view to handle. Methyl iodide is a liquid, so you can just drip it into the reaction mixture and you get your product. Now this is going to be your last step. We're not done with the synthesis by any way, shape, or form because we haven't used an epoxide, and that's part of what the synthesis says. We have to use an epoxide. So we're going to make this from an epoxide. So now your next step is to think about, if this is the alkoxide that we want, how can we put together an epoxide and a Grignard reagent to make this? Here's the thing to think about. This is really important. When you're using this kind of Grignard reaction, the new carbon-carbon bond that you're making will be one bond removed from the oxide part of the alkoxide. So not this bond is being formed, but the next one over. This one is the one that's being formed. We will see later on that there are reactions where this bond is made, but in this particular case, since we're using an epoxide, that's the new bond that's going to be made. So go ahead and write out what two reagents would you want to combine, one an epoxide and one a Grignard, to get this particular alkoxide. Again, stop the video, try to write out what epoxide and what Grignard would you use to make this particular alkoxide, and then let's go ahead to the next screen. Okay, so here's our product. This is the alkoxide that we're shooting for. Notice that this is the new bond that we're going to want to make, so we'll need a 1, 2, 3 carbon piece, 1, 2, 3, as the Grignard, and then this 3 carbon piece, 1, 2, 3, is going to have to be the epoxide. And since we want the oxygen attached to that carbon, we're going to want it also attached to that carbon as a 3-numbered ring. And then when this comes in, attacks the back of that carbon, pushes out the oxygen, that would be the alkoxide that you would want. So this is the combination of the Grignard, or you could use a lithium here as well, and this is the epoxide that you're going to want to use. Now finally, how would we make this Grignard from an alkyl halide? Well, that's easy. You can probably do that without even thinking about it, but I'll have you go ahead and write out how would you make this from an alkyl halide. So write out the step and we'll do it on the next screen. Okay, here we go. As you've learned, if you just take an alkyl halide and add magnesium, you get the Grignard. Now remember, you could also have used lithium here. Back up to that previous slide. You could have used an organolithium here as well, in which case then we're going to want to have a lithium there, in which case then instead of reacting this alkyl halide with magnesium, we would react it with lithium instead, and then that would work just as well. The complete synthesis then that you would write if this were a quiz question is as shown here. This is the target molecule. You make it from this alkoxide by reacting with methyl iodide. Then here's the key step. How do you make this alkoxide? You make it from this epoxide and this Grignard or organolithium. But since the rules say you have to start with alkyl halides, not Grignard, you would have to make this from an alkyl halide, which this is one, and you would make it by inserting the magnesium in between the carbon and the bromine, by taking this off the shelf, adding magnesium metal, getting this, then taking this off the shelf, throwing it into the mixture and getting this, and then taking methyl iodide off the shelf, throw it in, and get this compound. Also remember that both the alkyl halide itself and the epoxide can be synthesized from alkenes. So this is just extending the synthesis a little bit more. So in other words, what I'm saying is, what if in the previous problem I had suggested that you not be able to start with an epoxide and an alkyl halide, or only start with alkenes. So basically everything you need can be made from alkenes. So if you need to make an alkyl halide, which you typically will because you're going to want to react it with lithium or with magnesium. So how do you make that alkyl halide? You make it from an alkene by adding HBr or HCl. Okay? And also remember that you can make the epoxide itself also from an alkene by reacting with MCPBA, as I mentioned before. So notice that this is a complete synthesis. Let's say this were the compound that you were asked to make. That was pretty complicated, but it's not if you break it down into pieces. Remember, first you want to decide, is that an ether or is it an alcohol? In this case it's an alcohol, so you're going to want to start with an alkoxide, and in this case just add dilute HCl to it. That protonates this oxygen, gives you that OH. But then here's the key step. How do you make this from a Grignard reaction or an organolithium? Well, since you want to make the bond that's next door to the carbon that has the oxygen on it, not this bond, but this is the new bond you want to make, you're going to want to start with your epoxide stretching across this bond, so this epoxide, and you're going to want to start with the organolithium or Grignard that has that group and with the metal attached on that carbon, so lithium right there. So you just use that epoxide and that organolithium or Grignard if you choose, and you put them together and you're going to get this. Now one thing that looks difficult, fancy here, is that you get this trans relationship between the alkoxide and the new carbon group that you've added onto that carbon. And that's just because this is on a ring. And so basically here's what happens. If you have an epoxide on a ring, when the new Grignard attacks the back of it, you end up with the oxygen on the front of it. So you'll always end up with the two groups that you're going to have on that new ring being trans to each other, so you always have a dotted line and a wedge in this particular situation, if it's on a ring. If it's not on a ring, you can't tell because it's rotating around that bond all the time, so you can't really tell if it was a trans or an anti-addition or not. One other thing to notice here is that this, since neither one of these is chiral, you would typically get both enantiomers of this and both enantiomers of that. So that would be the end of the synthesis if that were it. But if you had to make these from an alkene, as I'm suggesting in this case you would have to do, how do you make this epoxide from an alkene? Use MCPBA on that alkene. That's easy enough. You remember that reaction from the alkene chapter. And how would you make this alkyl halide from an alkene? Well, you would add HBr to this alkene because you want the hydrogen to go there and the bromine to go there. In other words, use it would be a Markovnikov addition. So this would be the complete synthesis if this were the target molecule and you could only start with alkenes. Now, what I'd like you to do at this point is do the whole synthesis, basically the same kind of synthesis I just outlined for you, to make this compound right here from an alkyl halide and an epoxide. So this is not going to be the alkene part where you have to make those from alkenes. You can go ahead and start with an alkyl halide and you can start with an epoxide. So analyze this molecule and see how you would put it together using a Grignard or an organolithium and an epoxide, and noticing that there's an ethyl group on that oxygen. So at this point, pause the video, work real hard, come up with a complete synthesis of this, and then we will answer on the next screen. Okay, so here's your synthesis. This is the target molecule. We're going to want to start, or at the last step in the synthesis, start with an alkoxide and put that ethyl group on just as ethyl bromide. So that's really kind of a trivial step. That's just putting that ethyl group on. But the important step is how do we make this alkoxide from a Grignard and an epoxide. Well, again, notice it's not this carbon-carbon bond that you're making, it's this carbon-carbon bond that you're making. So split your molecule in half right there. This part will come from the Grignard, so there's that part attached to the Grignard. This thing, this whole part, including the oxygen attached to that carbon, is going to be your epoxide. So there's your epoxide. Notice that this skeleton right here is this skeleton right here, and this skeleton right here is this skeleton right here, and the key is that that's the position where you're making the new bond, right in there. So here's an epoxide and a Grignard, and then since the rules say start with an alkyl halide, we would make this Grignard from this alkyl halide plus magnesium. Now, what if the question had said to start with alkenes only? Well, again, just to be clear, this epoxide is not an alkene, so we would need to make it from an alkene by using MCPBA, and this would be the alkene that you would start with. This alkyl halide is also not an alkene, so we would need to make it from an alkene. And notice in this case, if we were to add HBr to this particular alkene, it would end up with bromine on that carbon, not where we want it, because it's a Markovnikov addition. Well, you may remember, we didn't spend a lot of time on it last semester, but you may remember that if you start with an alkene and you add HBr, but you put in some peroxides, it goes anti-Markovnikov, so it switches the orientation of the hydrogen and the bromine. So instead of hydrogen going here and bromine going there, which is what Markovnikov would say, we get the anti-Markovnikov addition. So hydrogen goes there and bromine goes there, so you end up with that alkyl halide in that position. Just another little thing to keep in mind if you want to, and it's a useful thing if you want to make an alkyl halide from an alkene, but you need to do anti-Markovnikov, just throw in some HBr. And then another small detail here, since it says we can only start with alkenes, we can't really start with this. We would have to make that from an alkene, and that's easy enough. Just start with ethylene and add HBr and make that. So here's the complete synthesis of this target molecule, starting with only alkenes. That alkene, and that alkene. Well, it turns out it's just the same alkene. It goes in both directions here to give you that epoxide and that alkyl halide, which then you make the Grignard from, which then you react with the epoxide and you get that. So here's how it would work in the lab. You would start with some of this compound, that's called isobutylene. You would add MCPBA and make that compound. You keep it, set it aside. Then you would take some more of this isobutylene and add HBr with peroxides and make that compound. Then you would take that compound and throw some magnesium in to make that compound. You would then combine this one that you'd set aside before and this one to make this alkoxide. You would then throw in some ethyl bromide that you had made previously from ethylene and HBr, and that would give you this target molecule. So that ends the presentation for today. Thank you very much.